It's already 32. It's TCPM in this room, and if you are interested in TCPM, please sit down or leave. X or. Are the presenters here? Michael's there.
Yeah, I think we can start.
Okay.
Well, no problem.
Yeah. Okay, this is TCPM. Welcome. My name is Michael Tuxen.
My name is Yossi.
My name is Michael Schorf.
So, can you do the next slide? Maybe I can. This is the note. Well, it applies not only to this session, but to every session, so you have seen it. We don't need a note taker. Thank you for Richard and Gori for be willing to do that. Michael is doing the JavaScript. And if you're going to the mic, state your name and make sure that the note takers can see your badge if they don't know your name. So that's the agenda. We give a working group status update. We have talks or presentations regarding 3 working group documents, RFC 2140 bis, the RFC 793 bis, and a document which is at the end of the last call period, the converter draft. And after that, we have several presentations regarding non-working group documents. One is about HighStart++, then 2 presentations regarding Yang. Gori will say something generic regarding congestion control, and at the end we have a presentation regarding a new TCP, a proposed TCP feature called TCP pull. Are there any requests for changing anything? If that's not the case, then we will follow that agenda. We have a couple of documents. The first one the shepherd is Michael, so I pass the mic to Michael.
Yeah, so the first document that we are about to finish is the TCPM converter one. So for that, I've started a working group last call. You see here on the slide that I've put in the word almost finished. Almost means that I'm basically waiting for confirmation from Phil that his pretty comprehensive review has been addressed. Other than that, I think we are fine. That is, my plan is to close the working group last call once I have this confirmation from Phil. And then we will move on. We will have a presentation on this draft later in the session. But as I said, I'm going to close the working group last call once I have the confirmation from Phil that all comments are addressed. And finally, I've done this on the list already. I just want to give a heads up. We have seen as part of the last call an IPR declaration. I assume that you're all familiar with that. So if there's no comment on that, we assume that that's not an issue.
Okay, so then we have a document accurate ECN. The working group last call for that is planned soon. Soon means we hope to get it done such that the working group last call ends before the next IETF. We have generalized ECN. That document has been updated. We have the RTO consider document that hasn't been updated, but since the last IETF, but we found two reviewers, Gori and Jana, have said that they will review this. We have a document shepherd for this, Yoshifumi, and so we hope that we get something done by the next IETF. And Bob is at the mic.
Hi, Bob Briscoe. I just wanted to ask on generalized DCN. It's been ready for working group last call for about 6 months. We have 3 IETFs now. What's happening?
You got a list comment on that one.
You got a what?
You've received a list comment on that one.
From you, is it?
No, not me.
Okay.
Check the list. There's a comment on that one. So please work on it.
Then we have two BIS documents, 793 and 2140. We have presentations regarding them. And the last document, Tcpm rack, has been updated. It seems to be stable, and we will figure out how to progress that document.
Hi, this is Praveen. I had a comment on the rack document. So it seems to be stable. I think we gave some feedback and that's been updated. So I think it would be it's very close to last call in my opinion. Other than minor editorial fixes, it seems ready to me. So what do the chairs think about that?
Basically, the chairs share that view. So we will contact the authors and see how to progress that. It would be good if you can provide the feedback to the list or to the authors. Probably better to the list.
We'll do that. Thank you.
That's the last slide. Yeah. So that's the last slide. So this means we go to the presentations. One note, we have a packed agenda, so please try to stay on your time limits. The first one is Michael on RC 2140 BIS. On stage.
Okay. Yeah, 2140 BIS, update to 2140. Next slide, please. Oh, yes, I can do it. Now I do it, but that doesn't really work. I've seen that before.
Try to focus.
No, I mean it works, but in a disaligned way. That's good.
Okay.
Got it. Okay. I guess one important thing to point out about that slide is the number 06, which means that this thing has gone through several updates and reviews and comments in this group already before adoption. That was because at that time we were asking for BCP, and that's no longer the case. Now it's informational and adopted as such. Quick list of some updates that we made. We reissued it with the correct name. We cleaned some orphan references to TCP. There was a lot of some ancient text in this draft that really had to be removed from 2140. Moved references to the informative section and updated section 2, updated to clarify that there is no impact on interoperability, and updated Appendix B as per request. So regarding next steps, we as the authors thought this through. We don't find very much. We believe this is pretty much ready, except there's one thing that we would like to include. The document discusses ensemble sharing and temporal sharing, right? Sharing ensemble is when you have parallel ongoing TCP connections and they would share information between them, and temporal is connection is over, new connection comes and it should learn something from the previous. Now, it just talks about these things and it doesn't really say anything about time. What does later connections mean, right? It doesn't discuss timescales. It doesn't discuss what is successful sharing. It's resolved by TCP convergence. So we plan to add a short section on these things in the next version. That will talk a little bit about how long TCP information is valid, which is very much dependent on what information it is. To give you an example, RTT var, for example, that reflects the current traffic behavior and is probably something that a week later makes no sense at all. TFO state, well, okay, a week probably is too much for that as well, but it does reflect the state from the peer and the path state. So unless the path changes, and unless the peer is upgraded or changed, that may be valid for a long time. You know, it may actually even make sense to keep it for a week to just try it. So these are two very different cases. And if you have some very long-lasting state, this may also benefit from special consideration. There are some constants that you may find over time have never worked. You know, if something never worked in a week on the same path with the same host, with the same destination, and the host is maybe not a mobile one staying in the same place, at some point it may make sense to start adjusting them. So there are some ideas that come from a previous draft from Joe Touch. This automatic adjustment of the initial window. This is just an example. Considering the initial window, right now we have this experimental initial window 10. We have some hosts using larger values. We have some hosts using smaller values. The question is simply if you could be a little bit more dynamic. I think this is a good slide to remind readers that this is an informational document, so we're not proposing an algorithm that would be, you know, recommended for anybody to implement. It's just a description of possibilities. Well, so if it, you know, for instance, a very large initial window never worked to one destination for a long, long time, it probably isn't really useful to keep. If the sender's congestion window always gets much larger than the initial window is, you know, why limit it to 10? Maybe if you do pacing as well. The interesting thing here is that adding some dynamicity to this would automatically do an experiment and auto-adjust to the environment. So that is in line with this other draft from Joe. If you would have a node on a slow network connection that has a small, a small node, that might just never increase its initial window, even over weeks or months. So that this draft talks about, you know, long time scales. My own office machine, where the network is permanently upgraded together with the backbone, that might dynamically change the window. So these, you know, considerations may make sense. Regarding these things, there are different types of feedback that can influence this dynamicity. Currently, this is all convergence-based. The end values affect the future predictions simply by how the statistics aggregate. But there are other ways that could be done. We would call them implicit and explicit. Implicit would be a matter of tracking whether initial conditions persist over a connection. Explicit could be a very specific thing, like looking at a particular packet exchange. Again, this will be just a discussion of these possibilities. And that's it, I think. It's last slide. Questions, comments?
So Gary Fairhurst, yeah, I'm going to talk later, but I'm curious to know what sort of numbers you have from other RFCs to suggest these time periods, or whether you're just going to say, oh, we can do it in future. So did you come across any numbers to say how long you think a path's valid?
I did not.
Okay.
How many people have read that document? Okay, so give it a read. I guess you want to change. You said you want to update the document.
Yeah, to include this.
Yeah. Okay, so then we are looking forward to a new version. Thank you.
All right. Thank you.
So that one is Wes.
Can you hear me?
Yes.
Excellent.
Oh, okay. Please come.
We're trying to get the slides up.
I can see them. So, yeah, I'm Wes, and it's nice to be virtually meeting today. I haven't been able to make it in person for a while, but have been working on RFC 793 Biz for quite a while, and thought it was really important to try to talk virtually about it today because, well, I think it's needing to get ready for a working group last call soon, because it's getting to the point where the things we identified to do are pretty much done, and there's not a lot of churn happening. So with that said, I will go to the next chart. And I wanted to take a minute just to, because we haven't been talking about this at the past few meetings much, just give the background so people remember what we're trying to do. So RFC 793, everyone hopefully knows, is the TCP specification. It's been around for a very long time and was never actually updated fully, although a lot of things updated partially. And so several years ago, working group decided to adopt an attempt to update it. And to make that tractable, we said going in, sort of the approach is to not open up any new topics really, but just to focus on dealing with accepted errata. So things that have been submitted over the years and collected through the RFC editor's errata process, and then the area directors have talked to the working groups usually and marked them either verified or held for document update or rejected. We're not going to put the rejected ones into the document. Then we collected all the other RFCs that update parts of 793 and tried to make sure that those updated parts got reflected. And most importantly, we're not opening this up. Like there was some discussion early on about changing the semantics of something like the options length to do long options and stuff like that. Well, we're not chartered to do that in this document. So let's not talk about that today. The goal, though, that I've been using as editor of the document is to try to patch in the exact text from all of the relevant documents wherever possible, As you'll probably notice in reading it, that doesn't always lead to the most smooth flowing document, but the hope is that it prevents us from adding any mistakes. So next chart. So I posted a revision 13 that you can find on the IETF site now. And if you check the diffs, you'll notice there are only very small updates. And those are pretty boring. So adding a section reference about triggering this error report functionality for different ICMP types. There's one open issue that I have some notes around, and we'll talk about in a little bit. And then I had been marking the IANA considerations as like a to-do thing to analyze whether there were any registries that needed to be updated or something like that. But I did sort of a check on that and didn't think that there was anything further that needed to be done there. So I just sort of took away the to-do item. So with that update, the only thing I think that's left to fix is this issue that I'll talk about next. I have a revision 14 that's in work. You can find it on the in the Git repository that this Bitbucket URL there points to, and have already made fixes there to version 13 based on Greg Skinner's review that went to the mailing list, also Michael Scharf's review to the mailing list a few days ago, and a couple of other small things that I noticed. So the bullet at the bottom is actually already outdated because yesterday I added a commit that addresses Michael Scharf's review. So if you go to the next chart, one of the things that I did recently, a couple of versions ago, or revisions of the draft ago, that I wanted to make sure people were aware of while we're talking is all of the requirements language in the spec, wherever it says a should, a must, should not, must not, things like that, I labeled. And then with like unique IDs, so we have like must 1, must 2, must 3, and then you can find those labels in an appendix that lists all the conformance requirements. And that was borrowed from RFC 1122 that had a similar table of requirements, and then links to the section numbers where those were discussed. Labeling the specific requirement sentences rather than the sections is the main change here. So a couple people said that seemed useful, so I did it. And I didn't think it was going to be very much work, and it turned out to be more work than I thought. But it is done now. So next chart. This is an issue, and I'm hoping to get maybe a little feedback from the room on this. Talking about it with the chairs, we had 3 different readings of what RFC 1122 says. So maybe one of them is correct. The thing I'm going to propose, though, after looking at a bit more detail myself, is my proposal is that we actually don't do anything. But I'm going to talk just briefly to convince you that maybe that's the right answer. So I had something I marked to do in the document because I thought there was an issue around what's called the error report functionality in RFC 1122 describes it. Now, that's kind of a funny thing already because in TCP stacks with the socket interface, we don't exactly have something that matches the error report functionality, though there are sort of ways that what's described happens. So it's sort of a generic functionality anyways. Now, RFC 1122 to me looked inconsistent in one of the aspects of describing this error report functionality, because there is one section that says these reports must be triggered in the case of excessive retransmissions. So when there's the threshold for giving up, and there's another threshold for notifying application and also notifying IP that there seems to be a connectivity issue. So it appeared to me that the text said you must trigger reports when you hit that first threshold where there looks like there's a connectivity issue. And then I found another place in the document. So the section numbers are here in case you want to look them up in RFC 1122. There's another section, bullet D, and I say the second one because there's actually two bullet Ds in that list. There's a editorial bug in 1122. So that's even more confusing than it needs to be. But that second bullet seems to say you should trigger the error report. And of course, I was confused by this, and discussing it with the chairs a little bit. One of the things that came out is I think there's a possibility that we could interpret this as you must implement the functionality, and you really should generate the error report. And for reference, I wanted to look at Linux and Windows error codes and see what's done here, and actually couldn't find anything corresponding to this in terms of an error that's generated for the application to receive in either case. So I think that it may not be the most relevant thing to spend a ton of time on, but my proposal is basically to do nothing. If people have written stacks all these years based on the 1122 text and not been confused, then maybe my initial confusion was just unnecessary. So I'd like to ask for feedback on this. Do you think there's something to be done here, or can we leave it alone?
So this is Michael speaking from the floor. I would agree. I've read those sections, and I personally agree, do nothing.
Good. So I don't know if there's anyone else, but of course we'll relay this to the mailing list and check on that. Oh, Gory.
Gory first, even less helpful. I haven't read, but I probably agree from reading 1122 previously. It's got these problems, and I think you're doing the right thing. I will happily read again. Now you pointed me to it.
Thank you.
Michael Tuxen from the floor, just reading the text. Could it be that the should you were referring to, which you think is inconsistent, the should is, so the sentence is TCP should, and then at the end, when R1 is reached and before R2. So in this condition, it's a should, in the other one, it's a must.
That's a possibility too, yeah. My guess is, though, if we don't know for sure that that's what is meant, and if stacks aren't doing this, we probably don't want to change what the spec says.
Okay.
So if you buy that, I'll move on to the next chart. Michael Scharf had some great comments, and we don't need to go through them in much detail, but I sort of summarized them here so you could see that they're fairly minor. So adding cross-reference, deduplicating some text. There was some really historic language in there, left over from like the PDP 11 days and stuff. So that I have removed in the Git repository copy. And I also removed all the stale glossary terms about the ARPANET and things like that, which weren't actually referenced in the rest of the document. Anyways, so I think Michael, in his review, agreed these are quite small things, and in general, it's fairly stable and in good overall shape, which brings me to, I think, my last chart. The next one where thinking of the next steps, I'm pretty sure we're converging. So I'd like to propose that we're doing a working group last call soon so that people can check if we really are converged to a good place. And I was hoping that we could identify some specific reviewers who will be on the spot to take a close look at the document. And I was also wondering if we should request any early cross-area directorate reviews specifically so that we don't have anyone surprised that we're revising the core TCP spec somewhere else and wind up with difficult IETF last call comments or something. So I think this is the opportunity to ask the room for reviewers.
Yeah, thanks a lot, Wes, and I agree. So I'd like to open the floor here. First of all, are there any comments on what Wes has just said on the stability of the document? May I ask who has read a recent version of the document? So for the record, that is 2, 3. Okay. That is probably not good enough for going to working group last call, but we do need reviewers for this document. So, and I'm now asking the room, are there volunteers who would volunteer to read this document? And I can personally say it's easy to read. So it's pretty okay. So don't be worried. It's a good document. Okay, so I see Jana. Thanks a lot. I see Gori. Anybody?
I think Yu-Chung in the past has been a good reviewer.
Yu-Chung, yes, we had a private conversation. I hope that we convince him as well. Anybody else? Okay. Okay, Praveen on Jabber also agreed, so that's excellent. So then I think we have a decent list to start with, and we hope that we get reviews relatively soon. The final question that Wes has raised, this is something actually a little bit for our AD on the question whether we should early ask for cross-area review. I personally actually agree with Wes that that is something we might do in order to get early feedback from some of the other areas that obviously heavily use TCP. So what I'm asking, maybe I think Maria's in the room. So are there any thoughts on whether we should do that, or if that's a bad idea, or when we should do that?
Yeah, Kulevind. I'm not sure it's necessary because they mainly use TCP and you don't change the interface. And there will be at least I believe an ops review at the very end, which is probably the most helpful one. So that will happen anyway. So I'm not sure if it's necessary.
Yeah, I mean, the discussion that we had with Wes is whether ops and also security area, whether we should ask earlier because we don't know what will happen there, just to speed up maybe the process.
No, I don't think it's necessary for this document.
Okay.
Matt Mathis. Yes, I found your comment about people who might be using TCP a little bit ironic. I don't think there's anybody at the IETF who doesn't use TCP, but it behooves us to get it right. And if the application developers find something that we didn't find, we've really screwed up.
Okay, also the feed
and the IETF last call covers it all.
Yeah, sure. I mean, for sure we all understand that this document is essential for the IETF as a whole, and the IETF last call will be essential for this document. So that's well understood. We just have to discuss the best way to approach that and to make the process as smooth as possible and to ensure that at the end of the day we have an excellent document. So are there any other comments on the process here? So that doesn't seem to be the case. So my conclusion is that we have a certain agreement here in the room on proceeding this way, that is, we will reach out to the reviewers. Then once we have the review feedback, we will think about starting a working group last call. Of course, it depends a little bit on the timing of the reviews and the amount of review comments that we get. But in general, at least my intention would be that we get this off the table as soon as possible, maybe already around the next meeting or early next year. So that would be my plan. Okay. Then there are no further comments, so then thanks a lot, Wes, and let's move on.
So the next presentation is about the converter, also remote. No, sorry, local. No, this is just a presentation. You wanted me to upload the PowerPoint.
Oh, I sent the PDF file.
I know.
Yeah. Thanks. Sorry. And then maybe remote doesn't work. Oh, it doesn't work? Yeah, you have to tell. You have to tell when you change the slide. Try that
This
one.
might not
probably might not work.
Well, point it in that direction.
If
No.
not work, yeah.
Okay, so then you have to say and we will change the slides.
Yeah, hello, good afternoon. I'm Sang from Korea Telecom. And in the meanwhile, the JRTT converter draft is in the working group last call. So I last couple of months, Korea Telecom and TEDRS prepared some proof of concept of the JRTT converter implementation of the real 5G. So I will talk about today about some results of the POC. Okay, next slide, please. No, previous. It's number 3 and go to the number 1. So the initial motivation of the JRTT TCP convert protocol is to provide a lot of the number of client TCP-enabled client uses multipath TCP because the number of client of the multipath TCP is much more large number than the number of servers. So actually, the client just wanted to benefit from the MPTCP, at least on the fraction of the end-to-end path, even in the wireless or wired or something like that. but the figure, looks like somewhat, broken up there. But anyway, so actually the converter protocol provides the generic one, because we can convert any kind of TCP options and for example, TFO, SEC, or something timestamp, or even including the MPTCP. So we are now in the Tcpm working group, so it could be acceptable in the generally. So next slide, please. So basic design of the ZeroRTT converter protocol is an application level protocol, and it is listening on the specific TCP port. Similarly, for example, web service or HTTP or something like that. And all of the commands and the responses are encoded in the TLB format, and it provides the more extensibility rather than the other kind of proxy protocol like a SAX or IP encapsulation or something like that. So actually the first command are sent through the SYN payload, and this information contains the actual destination IP address and port information. And because it uses on the middle of the three-way handshake of regular TCP, it provides ZeroRTT to minimize the delay to establish new connections. And also, the SYN-ACK message provides the responses when one of the three-way handshake. And because we don't use any kind of encapsulation or proxy-like protocol on top of the application, so we call it plain transport mode between the client and the converters. So furthermore, clients can run the TCP options supported by the server, and from the client to vice versa. So it allows the client to bypass all the TCP options to the server side in the middle of the converter. Next slide, please. So simple example here. So there's a client on the left side and the server on the right side, and the converter proxy in the middle side. So whenever the client wants to make a new connection of the TCP, they should have to do a three-way handshake, starting with the SYN message. So SYN contains the server IP and the port number, and the command is the connect. It's sent to the converter, and the converter then send the SYN message to the actual server based on the information of the TLB connect information, and waiting for the SYN-ACK from the server, and the converter return back to the client about the SYN-ACK message using the OK TLB, and actually this extended TCP option. So actually after that, actual data goes through the converter to the server, or by another direction. So actually on the data, there is no need to include any kind of TLB. Next slide, please. So for the proof of concept, Tejas and Katie prepared the joint collaboration to implement the engineering about the based on the draft version 06, but now at version 09, by the way. But in the client side, we use this open source client library and the Wireshark dissector to see the converter works on Wireshark or some engineering analysis. Which is you can see in the URL up there, and we compare the ZeroRTT converter protocol with the SAX version 5 protocol, and it works on the we implemented it on the Android smartphone, Samsung Galaxy S10 for the 5G model, and we use this engineering version of the firmware to modify some of the system command or routing priority. So for the ZeroRTT, we use the open source SAX integration. For the SAX version 5, we use Red SAX, which is commercially uses in the KT Telecom to our subscribers. And as you can see in the bottom, the left-hand side shows the 5G indicator, 5G only mode, and the right-hand bottom side shows the Wi-Fi plus 5G plus Wi-Fi at the same time, and we can use the multipath TCP together. Next slide, please. So the result. Actually, we tested in the actual real commercial 5G network, non-standard remote, 3.5 gigahertz new radio, control and user plane separation mode of the 5G core, and all the transport IP protocol is IPv6, and for the Wi-Fi, we use the 802.11ax for the Wi-Fi 6, and we used all together for the 5G and the Wi-Fi. And we compare the latency for the TCP setup time for both the RTT and the SOCKS. And actually, the metric is the TTFB, time to first byte, the time from the SYN send and receive the connection acceptance from the one of our gateway proxy servers. So Korea Telecom data center, in the Korea Telecom data center, we installed the ZRTT converter protocol supported HAG, hybrid access gateway, which is modified by the DZRS, and for the SOCKS, we use some commercial version of the mobile MTTP proxy, and we compare it to that. So as you can see in the graph, the leftmost is the ZRTT converter multipath mode. Actually, at this time, we use the Wi-Fi as a primary route, so we can gather the 27 millisecond in average of the latency. And for the 5G, 64 millisecond for the ZRTT converter latency. And for the SOCKS, compared to the ZRTT, you can see for the 5G only case, more than 3 times more than the latency is more higher. And for the multipath TCP mode of the SOCKS, it is somewhat shorter than the 5G only mode. It's because in the multipath TCP, after the 3-way handshake of the TCP connection, the SOCKS protocol procedure is some portion of the SOCKS protocol goes through the 5G, and another portion of the procedure go through the Wi-Fi. That's why the latency is somewhat smaller than the 5G only mode. Okay, next slide, please. So this is the last slide, and we compare the signaling of the ZRTT convert and the SOCKS V5, and in the left side, from the converter's client side to the proxy, we require the 1 RTT, just the TCP SYN-ACK and the ACK. And from the converter proxy side to the server, we need the 1 RTT. And by the way, SOCKS version 5, because we are using the authentication mode, we need 4 RTTs from the client to the proxy side. Each because at least 4 RTT, because some of the SOCKS procedure functions requires some processing time. It can be not piggybacked by the push message. It's at least 4 RTT. It can be more than the 4 RTT, and the plus from the MA proxy side to the server, it requires 1 RTT. So just compare the RTT in the figure. The ZRTT can be much less short latency than the SOCKS version 5. So this is the end of the slide. And any question?
Yeah, thanks a lot. Are there any questions on that presentation? I would have one, mostly as document shepherd. So are these prototypes, or is this production deployment, or do you plan for doing a production deployment of that?
So actually, we have a commercial service based on the SOCKS version 5 for the MTTP. And if it is possible, actually, I'm from the KT lab, so I need to talk about the advantage of the ZRTT, and I would like to ask the marketing department, and and the Samsung also on device vendors also. So we will. and we are preparing.
Okay, okay, thanks a lot. So are there any further questions?
This is Yoshi.
Yeah.
Just out of curiosity. So you are using open source socks on the converter. So you can, while you don't have a sock authentication in this signaling graph?
Yes, actually, because we need some time to implement this one. So actually, we can insert some authentication message in the TLB together with the SYN or SYNAC or something like that. So we are preparing of that is another draft, and actually we need a time. So I didn't implement that kind of authentication for this one. Yes.
And one more thing is, SOX version 6 try to support zero ITT kind of stuff. You might already know it. So it might be interesting if you compare SOX 6 and then converter.
Actually, in the SOX version 6, in the routing area or int area, right? Yeah. Actually, it requires additional extra handshaking after the TCP handshaking.
Mm-hmm.
So it is the generality is much more better than the SOX version 6, I think. So we should compare of that, together with later.
But it might be interesting comparison.
Yeah. Okay. Thank you.
Thank you for the talk. A point of information: SOX 6 is being considered as a possible work item in TSVWG. So comments on SOX 6 and its usefulness will be really appreciated over there.
So
that's not necessarily to the presenter, but to the presenter as well. Sure.
Actually, I'm not very. I didn't follow up the SOX version 6 fully, but the last time I in the KT tried to make somewhat similar to the SOX v6. All the connect and the authentication and the method procedure at the same time, just one procedure. So we can show that the latency is shorter than the actual SOX version 5. So actually, that make work. It worked. Okay. That's my comment about that.
Yeah, the experience on SOX 6 is well appreciated here. Yeah.
Okay.
Yeah, so thanks a lot. Also, this is very useful information. We often do this in TCPM. If we finalize a document, it's always good to have feedback from potential users. So thanks a lot for this very useful data. And as I said before, the working group last call for this document is about to finish. The only pending thing is I have to find Phil, basically, and then we are done with the document, and we will ship it to the ISG then. So thanks a lot.
Yeah, thank you.
So this terminates this section of presentations regarding working group documents. So the next one is Praveen with iStart++, and he's remote.
Hi, can you hear me?
Yes.
Hi, everyone. Today I'm going to present iStart++. It's a modified version of Slow Start for TCP. Worked on with others, but I'm presenting today. Next slide, please. So first, let's quickly recap iStart. So traditional Slow Start for TCP has a flaw. So it does exponential increase, but it can potentially overshoot the ideal sending rate by a lot. And this causes massive packet drops. And then TCP spends multiple round trip times recovering from those losses. Even if you have loss recovery algorithms like RAC, sometimes this ends up causing a retransmission timeout. So iStart is a paper that was published which had two schemes to solve this problem. So the goal here is to exit slow start early before the massive packet loss happens. So the paper had two algorithms. One was based on delay increase, and the other was based on inter-packet arrival. The original paper suggested that the sender run both of these algorithms in parallel and then exit slow start early. The problem is that the inter-packet arrival algorithm does not really work well because there is a lot of ACK compression happening both on the receiver because of things like RSC, as well as I meant LRO, and as well as the network doing ACK compression. The delay increase algorithm works, but we find that it has a lot of false positives. This happens because of latency fluctuations on wireless links. It also happens because there could be a large burst from another flow that could cause transient queue buildup, which could last multiple round trip times. And then the flow ends up exiting slow start very early, and then congestion avoidance will take a long time to ramp up. Next slide, please. So what is the delay increase algorithm? The goal is to keep track of the minimum observed RTT in each round. So for rounds where, so we keep track of this minimum RTT until the congestion window is higher than the minimum SS thresh value. This is to ensure that slow start does not exit too early. There's some protection in high start for not exiting slow start early. So the first few rounds, we do not exit slow start even if delay is increasing. Once that condition is met, then we calculate the ETA based on the last round's observed minimum RTT. And if the current round RTT is greater than a certain threshold from the last minimum observed RTT, then we exit slow start and we capture the value of SS thresh. I'm noting down the constants that is used in the current implementation in Windows. I believe that the constants are very similar in Linux based on mailing list discussions. Next slide, please. So why is this not sufficient? The problem here is that even if you do this only for the initial slow start, the slow start could exit prematurely because of the two problems I mentioned. So what High Start Plus Plus does is introduces limited slow start right after the TCP flow leaves slow start. So basically what we want to do here is for each arriving ACK, we want to still grow the congestion window, but not exponentially. So this is an additive increase, it's a large additive increase. And this will continue until the congestion signal happens, the next congestion signal happens. And then we enter congestion avoidance. So this is a phase between slow start and congestion avoidance. We do limited slow start. The LSS divisor we picked was based on experimental results in the lab, simulating various possible bottleneck buffer lengths, buffer sizes, as well as RTT and bandwidth. Next slide, please. So when we posted this draft to the mailing list, there was a very interesting suggestion by Neil Cardwell, so thanks to him. So on high BDP links, this can still cause the congestion window to grow too slowly if even if we do limited slow start. So the idea is to basically also start computing the congestion avoidance-based congestion window and take the max of the value computed by limited slow start as well as congestion avoidance. This basically, we were able to force this condition explicitly, and we observed that for high BDP links, this does end up helping. So the ramp up is much faster in cases where we exit too early due to high start. Next slide, please. So the current status is that this is deployed. This is on by default for all connections. I'm talking to you from a system that has this on by default. The fix for the high BDP links is also now in preview. So we expect to be also turn that on for the next release. The draft was actually posted to the mailing list. So please review and provide us feedback. We already had one review, but I'd appreciate if more people could review this and provide us feedback. In future, we would like to compare the other proposals for improving slow start, which is BBR startup phase, as well as pace chirping, which seems to be a very recent research on doing slow start by using pacing. And then any questions? And I would also like to ask the chairs whether we can adopt this document in TCPM.
Are there any questions?
Jana Iyengar, thanks for bringing this presentation, Praveen. It's useful. I was going to say that you said you're using a system that uses this right now, but we missed your startup phase. So we don't quite know how it went, but I'll leave it at that. I was going to ask you if you had any traces that you could show where you could show high-star ++ behavior. It seems quite promising, and obviously you've done measurements and you've seen this. You've probably seen a million traces. It would be super useful to see a few traces to understand exactly what the dynamics are. I'm also quite interested in understanding the convergence dynamics of high-star ++ with other flows in the network as well.
Thanks, Jana. That's great feedback. So yes, we would like to present more results on this. We do have lab measurement data. We are also currently working on metrics that we could collect more data from the wild to be able to compare actually in production systems, data from in production systems to see how effective this is. So we are currently working on techniques to do a very effective comparison from both lab measurements as well as in wild measurements. So yes, I will try to get you that data by the next IETF.
I appreciate that. Thank you much. I was also going to ask you a separate question. This is so high-star basically tries to figure out how to leave early, and that's useful. But there's also work that can be done at the beginning of high-star. I mean, this is still continuously, all of these, except for pace chirping, we have this exponential increase that happens at the beginning. Have you thought about changing that aspect of it?
So exponential increase actually is very, very helpful. So yes, because you're starting out fresh, yeah, you can use a higher initial congestion window and pace, but even then, for high BDP links, if you don't do exponential increase, then it's very difficult to figure out what the ideal sending rate should be. So anything slower than that, yeah.
Yeah, to be clear, I'm not suggesting removing exponential increase. I'm suggesting making it more aggressive.
No, we find that it's already too aggressive. That's the reason like high start helps a lot. And that's why high start ++ is also so effective, because under variety of network conditions, we find that this overshoots the ideal sending rate almost all the time. So, so it's actually too aggressive already. So that's the reason we are doing high start ++.
Just a last comment. I'm trying to clarify my point, which is high start is a way to leave exponential increase. What I'm talking about is pace chirping, for example, doesn't do that exponential increase up front. It does it, but in a very different sort of way. I'm trying to figure out if there are ways to combine those things, where high star ++ helps you leave when you believe that you've saturated the network, but you start off in a different way. But there are others formally.
Certainly possible, yes.
Yeah.
Certainly possible. At least for this draft, the goal was to actually document the implementation as is. So currently it's intended for informational status, but I do agree that there's a lot of like more possible research here to make slow start better.
Rod Grimes is an individual asking if you've run this on any networks that are CE marking to see if that avoids the bursty behavior at the beginning you're seeing.
So unfortunately, ECN is not widely deployed, and we don't turn it on by default. So we don't have data to suggest if it will help. But certainly, none of this changes response to congestion signals, right? So if you do get an explicit congestion signal, we will exit slow start. So and again, we will exit low limiter slow start as well whenever there's a congestion signal. So none of that changes. But no, we have not experimented with ECN.
Okay, I would like to see some experiments with ECN on.
I would comment to this, what Jana said about this using pacing and combining it with high start and IC. They are totally incompatible because high start relies on building queue and pacing, on the other hand, tries to avoid building queue. So it's hard to measure something you don't build. So.
Any other questions? That's not the case. Thank you for that. Praveen, you're asking for working group adoption. So the document is clearly within the scope and can be taken at some point of time. We would like to see measurement data before we do this.
Yeah, thanks. I will work on that. Thank you.
Okay, thank you. So the next one is also a remote presentation about Yang groupings for TCP clients and servers.
Yes. Hi, can you hear me?
Yes, we do.
Okay, great.
Remote stuff is working pretty well today. We are trying to bring up the slides.
Okay, great. I can see them. And I'll just say next as we need to move along. So hi, my name is Kent Watson, and I'm typically in the NetConf NetMod working groups, but today I'm presenting to Tcpm a draft that's been adopted by the NetConf working group for defining Yang groupings for TCP clients and servers. My co-author, Michael Scharf, has helped me with this, and I think it was adopted, we CC'd the Tcpm mailing list during the adoption poll after 104. Next slide, please. So firstly, it's understood that within TCP, there's simultaneous opens and peer-to-peer protocol. There's not really a client or a server, but nonetheless, here, and we refer to terms client and server. The client is the peer that's initiating the connection, and the server is the peer that's receiving or accepting the connection, having the open port. It's also noteworthy that within the NetConf and RESTconf protocols, sometimes the client is the controller or network management application, whereas the server is the device, which would be a router or a switch or firewall, for instance. Next slide, please. This is actually a problem that the NetConf working group has been trying to solve for roughly 5 years. The problem being how to configure NetConf and RESTconf clients and servers using Yang data models. So, designing the Yang data models that would produce a configuration hierarchy and in many cases translates out to CLI that could be executed on routers and switches or firewalls, or even now the protocols are being used by higher level applications. And so it actually it started off with one draft being the NetConf server draft, and then quickly folks said, oh, let's also have not just NetConf, but we need to do RESTconf as well. And then we can't just do servers, we have to do clients, and it became larger and larger. Next slide, please. Just a little bit about Yang data models. I think some of you may have a passing understanding of Yang. I know it's certainly popular within the IETF of late, but not everyone is up to speed. So just quickly, Yang is an IETF replacement for SNMP MIBs. It is a way to describe data. It's a data modeling language. Yang is to NetConf and RESTconf, or likewise XML, JSON, as for instance, a MIB is to SNMP, XSD is to XML, ASN.1 is to PIM, DIR, or BIR encodings, and ABNF is to binary. Hopefully that makes sense. Next slide, please. Okay, so just going back to the history, and interestingly, this slide's not formatted. It's supposed to be pretty ASCII art, symmetric tree there, but nonetheless, in the IETF 102 timeframe, the NetConf working group had the following hierarchy of adopted working group drafts. So the names that you see there are actually draft names. You would prefix each of them with draft-IETF-NetConf and then the name to get the full draft name. So there's actually a hierarchy of drafts. The top three each are just defining a single grouping, and then the bottom four are each defining definitely two groupings, one for the client and another for the server, and in some cases a third grouping representing a common grouping or certain amount of configuration parameters are being shared by both the clients and the servers. Again, this is what we had in the 102 timeframe. The note on the right-hand side is just mentioning that, in case you're not aware, the NetConf protocol has a mandatory binding to SSH, and then there's an optional protocol binding to TLS. And the RESTconf protocol has a mandatory binding to HTTPS, which of course is HTTP on top of TLS. So while you don't see the dependency arrows quite right. That's what they're trying to illustrate there. Next slide, please. The Yang models at that time defined knobs within the SSH and TLS groupings for keep alives. Of course, if you're having, I mean, we within those protocols, there's actually, the standard protocols is the client initiate, that this would be the controller application initiates the connection to the device. But with RFC 8071, we introduced this notion of a call home, which what really happens is the device is initiating the underlying TCP connection to the controller application, and then immediately the protocols flip. And so while the controller application begins as the TCP server, for instance, it then presumed or resumes acting like the SSH client or the TLS client on top of that accepted file descriptor socket. This is critically important because sometimes the devices are being deployed behind NATs, network address translation type firewalls, that makes it impossible for an external system to initiate a management connection to the device. So for the device to initiate the connection becomes critical. But similarly, it's necessary in some cases for the device to be able to ensure that the connection remains up, that it's persistent connection, and hence actively testing the aliveness of its protocol peer becomes important. And we felt that we could use the keep alive mechanisms as they're defined already in SSH and TLS to do that for us. However, Broadband Forum and Nokia were implementing this, and they discovered that TLS keep alives are not very well supported in the OpenSSL library that they were using. Even though there's an RFC for defining TLS keep alives, OpenSSL has not implemented it. And in fact, they partially implemented it and then decided to remove that partial implementation. So it may not get back into OpenSSL anytime soon. And nonetheless, Nokia and Broadband Forum were, asking if we could then enable keep alives at the TCP layer, which seemed reasonable. There was actually a discussion with TSV area, and Spencer Dawkins and others participated in that conversation. We came to the conclusion that supporting keep alives on every layer of a protocol stack is critically important, and hence there was no reason to not enable the ability to configure keep alives also at the TCP layer. But then the question was how to do it. And next slide, please. So in the 103 timeframe, we started to discuss how we might be able to create additional protocol, groupings, Yang groupings for these other layers. Again, this graph is not, the picture is not lining up nicely, but essentially a TCP client server draft that would define groupings for TCP and likewise HTTP and HTTPS. The idea here being is that then each layer having its own grouping can define the configuration for the keep alives at its own layer. And this actually is quite good because every protocol has slightly different ways of configuring its keep alives. And so enabling the configuration or the definition of the configuration to be co-located with each protocol layer was the right way to go. Next slide, please. That particular slide, the previous one, you don't go to it, but while I didn't say it at the time, it was kind of representing an is-a relationship. So for instance, if you instantiated an instance of the HTTPS grouping, it would in turn instantiate an instance of both the TLS and HTTP groupings, and then in turn they would instantiate an instance of the TCP. So it's kind of an is-a relationship, to use an object-oriented comparison. But we found that actually the has-a relationship was better. And again, the slide's not showing it quite right, but you're on the bottom there is sort of a flat list of the various protocols that can then be composed to represent the various protocol stacks. So for instance, you could have TCP over HTTP by just grabbing the groupings from those two drafts. or alternatively, you can have TCP over TLS over HTTP just by inserting also the grouping from the TLS draft in between the other two. So the composition becomes quite nice. So that's the current, that's currently what's been published in the 104 timeframe. Next slide, please. And just to go a little bit in detail of what the current draft defines, it is defining 3 Yang modules. There's a common Yang module, and in that Yang module it's defining 2 groupings. There's a common grouping, and then there's the what's called a connection grouping. So it's the connection grouping that's being used by the other groupings. The purpose of this factoring out of the common grouping is so that in case maybe someday in the future Tcpm would like to define a system grouping that would represent, for instance, the TCP configuration of the operating system itself. And so we have this common grouping that right now the only thing it's defining are keep alives. There's the connection grouping, and its only thing it's doing is using that common grouping. There's no additional configuration beyond that. Then there's a second module for TCP client, and you can see that it's well, actually it's not easy to see on the slide. I'm sorry about that. But it's defining essentially what is a remote port address and sorry, a remote address and a remote port, as well as optionally a local address and a local port. And then it's using the TCP connection grouping. So that's where it inherits keep alives. And then there's a server, but the slide is messed it up pretty badly, so I won't try to speak through it. But it's a very similar idea where it's inheriting some of the configuration from the common grouping. Hopefully the next slide works. Please, next slide. It's not that much better. So what's supposed to be shown here is the flattening of all those uses statements from the previous slide into the tree diagrams. And I think we might be able to see the top one. There's the client grouping, and you see the remote address, the remote port, the local address, the local port. And then you can kind of see the keep alives, but it gets pretty garbled. Unfortunately, that's very difficult to see. I really apologize for that. What's important here, though, is it's difficult as it is to see in blue. Hopefully, it's showing blue for you. The local bindings supported. That's question mark. So that's a feature. It's basically saying, does this device support the notion of allowing the local address, the local port, to be configured at all, or is it, for the client, for instance, or is it always the operating system that can wildcard, randomly select what the local address and local port should be based on routing parameters or wildcards. Also, and I know you can't see it, but in the keep alives, there's the idle time and probe interval. Both of these are currently UNT16s, and the resolution of those are seconds. So I thought, actually, Michael thought that this would be interesting for the working group to discuss if that resolution was correct and accurate, as opposed to, say, centiseconds or milliseconds. Currently, we're thinking seconds is reasonable for the purpose of keep alives for TCP clients and server connections. Next slide, please. Also not showing very well on the screen. Okay, so here's an example, and XML is being shown, but with anything that you're doing with Yang, you can also simultaneously support JSON. And in fact, there's another working group, COSI, that implements CBOR, which is a binary representation of instance data that conforms to Yang data bottles. But in this example, at the very top, at least we can get through some of it, there's a remote address. And notice here, it's actually using a host name. So on the previous slide, sorry, is there a question? Sorry, I thought I heard some feedback. On an earlier slide, it defined this remote address type as what's known as an INET host, which then allows for values as either being domain names or IP addresses, whether they're IPv4 or IPv6. So in this example, it's showing that it's actually a host name. Whereas, and you can't see it very well, but down below in the server, the local address is the IP address 10.20.30.40, and that particular type is actually a specific IP address. It's defined as an IP address, so there's no availability for it to be configured as a domain host name there. Also, in this particular example, you can see at least at the top the local address 0000. That's how it's been defined in the specification for designating wildcard address, and likewise the port is just 0 for designating wildcard address. Next slide, please. So this is an eye chart. We won't try to go into it, but what's I'm trying to be impressed upon you is that at the very top in the middle is the TCP common grouping, and then off to the left is the TCP client, and off to the right is TCP server. And then there's sort of a hierarchy of SSH and TLS and HTTP groupings that are dependent on them. Also, and then, mostly there's this feeding into the the netconf and restconf drafts I mentioned earlier, but there's also a syslog draft, there's a PSEP draft, there's a management connectivity draft, and now I understand in the Seaboard group they're working on, they want to add a UDP client server as well as a DTLS client server. So there's sort of what I guess what I'm trying to impress upon you is that the strategy of that's been put forth in this particular draft of having these 3 modules representing a common and a client and a server, that strategy is part of a framework, and the framework is rather robust, and it's been shown to be able to support the composition of some fairly complex configuration hierarchies. That's the main point of this slide. Next slide, please. Okay, and this is also the last slide. So next steps for the authors, at least, and also from the NetConf's working group's perspective, at least what our primary intentions are for supporting the configuration of NetConf clients and servers. We think we're done. Of course, we'd be willing to sort of allow the certain functionality or the feature set to be published as an initial RFC, and would hope that Tcpm actually would take over the any future updates to that RFC using biz updates as they would see fit. But before we can think to do a last call or anything like this, we'd want to first verify with Tcpm whether or not the model, even as simple as it is, if it's general and good enough for all the situations in which TCP Yang models could be used. And I guess that I'll leave that question to the room, or if there's any other comments or concerns, I'd be happy to hear them.
Thank you for the presentation. Other questions?
Matt Mathis, the only thing that bothers me about this, I mean, the Yang stuff and such seems to be fine, but this group spends a great deal of effort making TCP idiot-proof in the sense that the API doesn't expose things that people might think they could improve and therefore break things. And Keep Alive falls into that category. You generally people who want to muck with it don't understand what they're doing, and they actually don't want to muck with it. Now there are some exceptions, but in most places, many of the places where people have come up with exceptions, I have to be careful because the IETF is huge. For example, in BGP, at one point, TCP liveness was used to indicate BGP liveness. And it was realized that they needed to have a separate connectivity instrumentation protocol and not rely on TCP's notion of liveness for BGP's liveness. And I suspect we've been very, very careful here about that kind of thing. The knobs are you put it in the right gear and then you remove the handle. That's very much the mentality here. And so I have a little bit of concern about whether or not this is going to invite people to cause breakages because they try to adjust things that they shouldn't adjust.
Can you stay here? Michael Turkson from the floor. Reading the description of Keep Alive, so you're specifying a time after which the TCP connection gets dropped if there is no response from the peer. It's idle time times 60. I don't know where the 60 comes from. The value you put in is in seconds. The outcome is in seconds. So I don't know. And the other one is, does the keep alive timer, if you have no response, is there exponential backoff? And if there is, then this formula is wrong, because it does assume that you don't exponential backoff the timer.
I don't think there's backoff in the keep alive. There's backoff in other timers, but not keep alive. But my impression is that it was designed not to rely on getting errors. Boy, this was a long time ago. This is 20 years ago that this was worked on very hard. The design of the keep alive is not to determine if the network is healthy. It's to make sure that connections which are completely passive, where the other end goes away, eventually get reaped. It was solving that problem, not determining whether or not the network is healthy. And so servers turn on keep alive to make sure that if the client just evaporates and the server has no pending data, the server eventually dies. It's not the usual liveness question that people think about.
Okay, so just to respond to a couple of the comments that were just made, I didn't go over it because the picture was rather garbled on the screen, but there's also a feature statement for whether or not the server supports keep alives at all, which on a client or server basis could be enabled or disabled. So on a per implementation basis, if they don't want to support those configuration knobs, they can completely disable them and they won't be available for users to configure. Secondly, there's the ability, you can, the keep alive is defined as what's called a presence container, which means if you just put keep alives but don't configure any of those three knobs underneath, then the default values kick in. So there's hopefully sane default values, and again, people wouldn't muck with them and get themselves in trouble. Lastly, that description statement, the times 60, maybe I need to revisit that, and it could be wrong, especially in the light of exponential backoff.
Final statement.
Yeah, Mia Kulevin, just to answer a couple of things. So keep alive is actually something that comes up very often and people can do wrong because you can configure, instead of the 60 second, you can configure, I want to keep alive once per millisecond, right? And that breaks your network. So it's really something that you should be careful about. There is an exponential backoff. That's when like your keep alive fails, you don't get a reply. Then you exponential backoff. But if it's running, everything is fine. You just can overload the network easily. But I'm glad that you said that there are defaults and that you can disable it and probably also put a big warning in it. Don't do anything stupid here, right? So just be careful.
Okay, thank you.
Thank you. Next presentation is Michael. You get 10 minutes.
Yeah, hi. My name is Michael, speaking here as individual, and that is a follow-up presentation also talking about Yang. So next slide, please. Oh, okay. Actually, it would have been good to have the presentation that you have just seen in the last IETF meeting, because this would have simplified a lot, and there was a little bit my mistake that this didn't happen. So, but in general, we see that there is this trend in certain other working groups that people feel a need to configure certain parameters in Yang, most notably the things that you can configure via socket options, and the keep alives are actually one such example. There are also other ones. Also, for example, there is at least one Yang module out there that configures the MSS, which is also something that some stacks expose, for example, by a socket option. So we see TCP parameters in Yang modules increasingly, and that somehow raises the question to us as TCPM working group, so what do we do with that, and is there a bigger problem to be solved? And I explicitly raised this as an open question because I believe that we should discuss this. I have not fully came to a conclusion. But in general, if we look at the TCP stack, we do not only have the parameters that are exposed by a socket option, but obviously we also have configuration parameters, and typically that this is at least subdivided into a global configuration of the stacks, such as whether you enable, for example, ECN or SEC. And in many stacks, you also have interface-specific parameters, for example, something about the MSS, or maybe related to the MTU or other offloading-related parameters. So there's a bunch of parameters out there. And this raises the question, so is there something to be done in this working group? So next. In the last meeting, I promised to come up with a survey if something is doable, because there was clearly a question in the last meeting whether this is something that is actually doable. And what I've done in the most recent version of the draft, I've looked at a couple of stacks, also 4 different ones, in order to identify if there's any commonality in the configuration, in particular beyond things that can be configured by the socket API. And what you see here on the slide is a summary of what I came up with. So I've looked at 4 different stacks. Not all of them are configurable by Yang, so I've also looked at some host operating systems. And I've tried to identify a couple of configuration parameters that are common. And you can see there are a couple of them. As for example, that's not a big surprise. Stacks that support, for example, the sec option typically have a Boolean or similar to a Boolean parameter to turn that on and off. And the same applies to other standard optional TCP functionalities, such as timestamps, for example, parse-MTU discovery, ECN, and there are a couple of other parameters here. So you see that there is some commonality in what you can turn on and off, for example. Of course, the exact way how you do that, so for example, whether it's a Boolean parameter or whether it's an enumeration, so that depends a little bit on the system, but there is, at least for very basic functionality, there is a similarity between stacks, at least for these very basic things. And that obviously could bring us to a Yang modeling for that. So we could, at least for such simple things, we could decide to propose a Yang model that includes those optional parameters such as stacks. So I've shown here one such example. So we could define, for example, a Boolean parameter in Yang for enabling or disabling sec, and then there would be a standard way in Yang for having that configuration. The benefit of doing this would be that this could be used in various other Yang modules, as opposed for devices, or, for example, also in other protocol environments, as a TAPS would be, for example, one such profile, but this could be useful. They could reference those standard definitions if they feel that there is a need to deal with such TCP configuration parameters. And the proposal here would be just to define the grouping, similar to what you have seen just in the previous talk. So we would not define a full data model here. We would only define groupings for certain parameters. And because this allows to reuse these things in a lot of different use cases. I've shown that there are a couple of parameters that are reasonably common. There are also, I've looked at other parameters there beyond what I've shown in the previous table. There are other ones that are often available in stacks, but the exact way how it's configured starts to depend on the different stacks. So you can see here examples like the delayed act timeout, the initial RTO, or some very basic parameters of the retransmission engine are often configurable in many stacks, but the details start to be different. So if you look at in the individual way how to configure that, each stack has found a different way to configure that. Of course, also in those cases, we could come up with one reasonable way to model it, but the risk that this does not have a one-to-one mapping to the specific configuration of a stack gets higher. And then, of course, there are huge areas of a TCP stack that are very specific to the implementation. Examples of, for example, everything that deals with buffers or with flow control. So there are a lot of heuristics out there, and that's typically very specific to the stack. Also, for example, the way how congestion control algorithms are implemented is obviously very specific to the stacks, and it's very hard to come up with a common set of parameters. So at the moment, I don't try to enter that space because I see a huge risk to boil the ocean in going there. And as I said, this is what I've shown on this slide, is what I promised to do in the last meeting. Do you have a question here or on the next slide?
I was going to make a comment on your last slide about the fact that heuristics are evolving. What we did in RFC, gosh, I've forgotten the number. The TCP extended information MIB is the introduction specifically says that if you have precise knowledge about how the implementation works, you understand precisely how the variables are defined, but the variables are defined in ways that are sort of generic. If you don't understand the details of how the stack works, you can only just make sort of generic assumptions about them. And that the standard for the instrumentation was not to preclude, specifically not to preclude evolving the heuristics. And so there's always example language of that, which you're welcome to steal.
Yeah, sure. Of course, I mean, that is quite related work. I've looked at that document. I'm not reusing the heuristics because this would be operational data, and I'm not
4898.
Okay. Anyway, as I said, what I've done here is what I promised last meeting. So I've basically completely rewritten the document. I've also added a new co-author. So I'm looking for co-authors who have a background in that space, and Vishal volunteered to help me with that. If you look at the model right now, you will see it's not an actual Yang module. It only has text right now, but one of the potential next steps would be to formalize what I've just said, to come up with actual Yang grouping definitions along the lines of what I've just presented. So that would be the natural next step if people here in this room believe that this is something that's valuable. And as I said, I mean, the key question that I have is to specifically also to implementers in the room if they feel value in further working in that space along the lines of what I've said, or if the general feeling in the room is that this is probably something that gets too complicated. As in the last meeting, there was a very mixed feedback on that, and that's why I'd like to open the floor to this question again. So please feel free to comment if you find this useful, or please also feel free to comment if you think that this will not go anywhere. So that would be excellent to say it now. And that's the last statement that I want to say. Feel free to comment.
So intended status is informational?
Well, at the moment, the intended status would be standard struct because Yang models typically are standard struct. I've said last meeting, of course, Tcpm has pretty high bars for standard struct. That is definitely something to think about. I've used your standard struct because that would be the default in the rest of the IETF for Yang modules. But yes, of course, I mean, standard struct in Tcpm has a certain implication, and that's definitely something we would have to think about.
Microtuxin, I can't comment on the usefulness of it, but I think what would be useful is to include the, to make the congestion control module selectable and the loss recovery. Loss recovery, rec.
Yeah, the issue with that is then we would probably have to have something like a list of congestion control algorithms or like that. And as coming up with a standard specification for that is something that would definitely require some thinking. But I mean, I can give it a try.
At least make it selectable, even if people can use platform-specific values.
Mahesh Yetanandani, two comments. One, to the point of usefulness, absolutely. If you don't do it, as you've seen, other models are going to define the parameters they need, and then you'll be left with a scattered list of parameters that other models or other authors are going to find difficult to locate. To the other question of standard struct, absolutely, if you're going to include a Yang module, even if it's just groupings and no containers, it has to be a standards document. Thanks.
Okay, thank you.
Okay, thanks a lot.
Thanks for the presentation. Gori is next.
I'm Gori Fairhurst. I'm going to be talking about a draft which is draft Fairhurst TSVWG CC. Why TSVWG? Because it's supposed to refer to all transport protocols. Why here? Because TCPM has a clue about how to design congestion control, which is what CC means. So let me tell you a little bit. Next slide. No, I can try this. You can try it. So this is an overview. You've probably noticed the IETF has said quite a bit about congestion control over the years. So it's clear if you want to design something that does congestion control or maybe doesn't, which document to look at, isn't it? Well, I spoke to Janet at the quick interim, and we thought, yes, the answer to this must be true. There must be a couple of documents we could just point to. And we can just write quickly a 4-page summary of these are the key principles, not the details, but the key things you must do if you design a congestion control. And then we could write this document. It'd be so short that maybe we don't have to publish it. We can just include it various places and say, play well and do this. It took more than 4 pages when I tried and more time. So I've done some work, and that's what's in this particular internet draft. The draft revision started with 00. I just kind of consumed RFCs. I thought that each RFC would be about one thing, and then I discovered that many RFCs talk about something for a few paragraphs, and then another RFC talked about the same thing for a few paragraphs using different language. But I looked at 26, and there's probably a few more. And then I got fed up because it was a lot of time. And then I went back to it because I thought maybe there's something useful here. So I wrote 01, which was the same text made more coherent by getting other people to read it and also by me leaving it for a while. And it went shorter. So I thought, oh, yeah, we're onto something good here. Then I thought, actually, I'll present this at the IETF, which is where we are now. And there's still a few annoying typos. I have those in my XML version. I'd be happy to fix those if people think this is useful. So what is it? So section 3 of the document is the first bit where there's important stuff. It talks about the principles of congestion control. If you've been in the IETF for a while, you'll remember there's a BCP written by Sally about 20 years ago. That probably isn't the best document to tell somebody how to run the internet, but it might be. So let's try and write down some principles. I picked 3 major principles. There's a diversity of path characteristics out there, so be aware of that when you design something. There's something where flows are multiplexed and congestion happens, and that's important to know about. And it's important to avoid congestion collapse, which is Sally's main point. This is the real thing that utterly has to be avoided. The second one is a little bit about understanding about starving other flows out, and about how you apportion the bandwidth between them. But there's things in there. We have to read this, of course, if you're interested. Section 4 then provides some guidelines on performing congestion control. So this is extracts from the musts and shoulds of various RFCs, and it talks about connection initialization, what it means to have a retransmit timer, what an initial window might mean, which is a bit difficult to define, actually, so maybe it's worth trying. About using path capacity, about bursts, which we tried to ignore for a while, but we probably shouldn't be ignoring in the internet. But we don't want to be too prescriptive, but we do need to say a little bit about timers and retransmission, responding to potential congestion, which we could call incipient congestion, which might indicate it's not the same as persistent congestion, why we need to use slow start to get more capacity or what that might mean, about network signals and trusting them, and about protecting mechanisms, what it means to be on path and off path, which I noticed this IETF people started using different words for, so might be nice to have some definitions for these. Well, okay. My basic thing where I'm standing here is, have I done it? And shall I just file that and walk away from it? Or has anybody else read this? Would they like to read it? Do people care enough that we should actually update this and write this as a proper document? I'm happy to go through everything we have at the moment as input and work with other people to make this into a real guidance document. Do people care? Who would help me? Or I can happily write other things.
So this is Richard. So I do
Thanks
care.
for the very quick presentation question.
And I think it would be great. It would be great to have a document that is written in a modern style to point people to who have not been exposed to all the things and that is going on in real world networks. Thank you.
Thank you.
So this is Michael from the floor. I've read the document and I do care.
Okay, thank you.
Rod Grimes is an individual. I wish I would have read this document before I got here because I'm going to have to read it tonight. So thank you for making this document, and I would like to see it carried forward.
If you're looking for the wisdom in it, it may be in another version. There's still quite a few loops and things in this one. But thank you.
And this is Yoshi from Floor. I think this is very useful, and I support it. And thanks for writing. And then one question is, you didn't mention fairness in this draft. And then it might be tricky things, but I'd like to understand if this is intentional or not intentional.
I mentioned multiplexing and the idea that you had to multiplex and the idea you had not to starve. I mentioned that routers can do things to help you achieve these goals. If I didn't mention fairness, it was because I didn't find RFC keywords mixed in with the fairness that I thought had to be in here. But that is the sort of thing which we should talk about because it's important to say something. Probably we should say something about fairness, even if it says something that isn't a must or should do it.
All
right, Bob.
Bob Briscoe. I'd support this as a checklist.
Mm-hmm.
I probably wouldn't support it as trying to tell people the wisdom that you just mentioned that congestion control designers have got, because that's just going to be going on forever. You know, and also different people have different opinions on that, and you know, it will just become a churn of nothingness.
Yeah, okay. So now we're getting there, and especially now the gentleman's joined at the back of the queue. This all started in London with the Quick interim, and trying to think about how strong can Quick actually say you do any congestion control you like, providing it's reasonable. And then what the heck is reasonable? So I don't want to Bible about how to design congestion controls, but I would like to have some kind of reasonableness tests.
Comment from Praveen first. Praveen.
Hi. Yeah, this is certainly useful. I think it's very valuable to have like one document that has links to all the necessary principles, as well as links to other documents that describe congestion control. So I'm very supportive of this. Happy to review it and help make progress.
I love the idea of helping to make progress. Thank you.
Yes, Matt Mathis. I also second the idea. It's a really great idea. It needs to be very explicit that it's not exhaustive.
Yes, and it isn't.
And I would suggest using the words capacity allocation, and not the word fairness has got too much all sorts of other stuff around it.
The lines are closed off.
Okay, that's fine, Matt. I chose maybe if fairness didn't actually appear as a word anywhere, maybe that was not unintentional.
I've had one of my favorite papers, I accidentally used the word fairness, and I came to regret it later. So let's just say that.
Okay, I believe in fairness. I don't believe in equality. Oh dear. Let's not go there. John.
Where are the blue sheets?
It's all Matt's fault. So I feel partly responsible for this, but only partly. Gauri, you did the work. But thank you so much for doing the work, and I'm very I'm happy to see this work happen. I'm happy to review, and more than review, I'm happy to help by contributing text and by helping shape it. I agree that I maybe I didn't understand Bob correctly, but I actually don't want a checklist in the sense that checklists are going to be inexhaustive. They're not going to be exhaustive. And that's the failing in some ways. It's like it's never going to be exhaustive. So what's the point of having a checklist? If I want to have considerations, that's useful to me in this sort of a document. Maybe this could lead to test suites and other things that actually implement checklists. Not that we've done this before. I definitely don't want to instigate that work here again. But beyond that, I think it's super useful as a way to think about what is reasonable. I think that's a conversation we've not really had. We've had conversations about perfectly fair, but not what's reasonable.
So
I wanted to try and translate his comments because I think I agree with it. The problem with the word checklist is it implies that there's an algorithmic binary decision, and that's not correct. And a better word is considerations. Yes.
Thank you.
Yeah.
So I think you got your feedback that this is a useful document, and I would suggest get the discussion to the mailing list because we are running on limited time. So anyone, you need some?
Can I ask which mailing list? Because I chair that group, you chair this group. I don't. Can we please not do this on two mailing lists? This is killing my brain having multiple mailing lists.
And I chair a third group.
Yeah, I know. Go on. You want to do it on ICCRG? Discuss the standards implications of the.
I think so. I mean, again, honestly, is there anything standards worthy here?
Yeah, it's all the shoulds and musts extracted from all the standards and which standards which.
Let me ask a different question. What
can we sort this out
afterwards?
We sort this out after the meeting.
I'm happy to do that.
And we'll get you. So we have a last presentation. Anyone who has not signed the blue sheets, now is the opportunity. It might work.
Okay, hello everyone. My name is Carlos Gomez. I'm from UPC, and I'm going to present this new draft entitled TCP ACPUR. My co-author is John Courcroft from the University of Cambridge. So first of all, let's go through the motivation for this new document. It is well known that delayed ACKs allow reducing packet overhead under some conditions. However, it's also true that delayed ACKs may be detrimental to performance in some scenarios. So let's assume a segment that carries a message of up to 1 MSS. If the message does not elicit an application layer response and the second data segment is not transferred earlier than the delayed ACK timeout, then the ACK for the segment will be unnecessarily delayed. And this may entail a number of negative consequences. So for example, if the sender uses the Nagel algorithm, the sender may be prevented from sending more data while awaiting the ACK, and this may lead to high underperformance in high bit rate environments, as reported, for example, in the DNS stateful operations RFC. And the reason here is that in high bit rate environments, the RTT might be below 1 millisecond, whereas the delayed ACK timeout is typically 200 milliseconds. Then in another domain, which is the Internet of Things or IoT, devices or many devices typically exhibit significant resource constraints in terms of energy, memory, and other resources. And a device, an IoT device that sends a segment, needs to keep the segment in a buffer until the ACK arrives. However, the memory resources cannot be released until the ACK, which is delayed, arrives, and due to this delay, there might be problems if there's not much memory available, which might even lead to packet drops if subsequent packets need to be sent meanwhile. Also, IoT devices run typically on energy-limited sources, such as simple batteries, and depending on the technique used by the device for energy conservation, for example, if the device uses a radio interface, the device might stay with the radio interface on, awake, and consuming energy while awaiting the ACK, which is delayed. So the delay contributes to increasing the energy consumption and decreasing the lifetime of the device. In addition, the ACK delay might interact negatively with layer 2 mechanisms in some IoT technologies, where there are some specific opportunities for transmission and reception of packets. And if, due to the delay, some opportunity is lost, it means that the next opportunity will only arrive after some longer delay, which then in turn exacerbates the previous two issues. So we might want to consider solutions, and we might think, okay, can we, for example, try to disable delayed ACKs at the receiver if at all possible? And the answer is that perhaps no, that's probably not a good solution, because the receiver may interact with a variety of devices, and delayed ACKs may still work as intended in many connections. And even considering a specific sender, perhaps the sender may offer a mixed traffic pattern where delayed acts may work as intended for some part of that traffic. So a conclusion is that a solution to this problem should be at the segment granularity. So what we are proposing in this document is what we call the ACK pool mechanism, and it would make use of one of the TCP header reserved bits, which is defined in the document as the ACK pool flag. This would be more specifically the 6th bit of the 13th byte of the TCP header, and the mechanism would be as follows. If the sender wants to request an immediate ACK for data segment, then it sets the ACK pool flag, and on the receiver side, upon reception of a data segment with the ACK pool flag set, then the receiver, if it conforms to this specification, it must send the ACK immediately. There's a question? Okay. Then after the internet draft submission deadline, there was some nice discussion on the mailing list. There was good feedback, many good comments that were sent on the list. I would like to thank everyone for that. And I've tried to summarize the feedback on this slide. So one point is that, of course, one of the TCP header reserve bits is an expensive resource, and we are well aware of it. So that means that we need to carefully assess the pros and cons of this proposal, or perhaps some alternatives. Then also the use of the maximum MAC delay option was suggested. However, with that option, we understand there might be two issues. One is that it's an option that would not be a solution offering, a solution at a segment granularity. And on the other hand, this option entails an overhead of 28 bits, which might be not so good in some scenarios such as IoT. Then there was another comment or suggestion, like perhaps we might redefine the push flag as having the ACK pool semantics. This could be phrased as a TCP may not delay ACKs for data segments with a push flag, which in principle would be allowed by RFC 1122. Then there were some reports about how is actually the push flag being used in the Windows and Linux implementations. They set the push flag at the message boundary, and at the receiver side, neither Windows nor Linux send the ACKs immediately upon receiving segments with the push flag set. So it means that in these implementations, the push flag is not being used as having the ACK pool semantics. Then there was some concern raised that there are applications such as RPC or web that use many small packets with a push flag set that do benefit from delayed ACKs, because then it's possible to piggyback action replies. And in those cases, if we redefine the push flag as having the ACK pool semantics, then this benefit would be lost. Therefore, perhaps having a separate ACK pool flag would allow having both things, would allow using delayed ACKs in those cases where it's useful, and also separately supporting the ability of requesting immediate ACK when needed. And finally, there was another point made that selfish devices might want to always use this mechanism. Therefore, we might need some clear rules or recommendations on when this should be used or would be allowed. And finally, there's a security consideration, or at least one to be done here, which is that there's a possible DOS attack as a result of this ACK pool mechanism, especially on resource-constrained receiver, whereby an attacker may send a large number of messages to a victim node requesting an immediate ACK for each in order to contribute to depleting resources from the device, for example, energy resources. One approach to avoid this attack would be just ignoring the ACK pool flag. So are there, comments?
So comments, questions, yes. So when I read this draft, it was not quite clear to me what the exact problem space was that you want to address. So you mentioned IoT, and the other aspect that I was missing was we do have a couple of mechanisms, like for example DSAC and TLP, which could be exploited to exactly this point. Unilaterally, you don't need any change on the server side to extract this information more quickly if you actually need the low latency. So I'm wondering why those aspects have not been in this draft and why they were deemed unsuitable.
Okay, thank you. We'll definitely look at the mechanism suggested. And regarding the problem space, actually, there seems to be a problem in different domains. And there are the two examples I mentioned. One is the IoT, another one is high bit rate environments. Perhaps there are some other scenarios. So this is perhaps some more general problem.
I was exactly going to say that. I think this is a more general problem. As we haven't got much time, I'll leave it there. But I'd support work in this space, but things like ACK rate control from the sender as well could be folded into something like this. So maybe we need to start working on requirements for this before we.
Yeah, so we closed the queue after Praveen, who has entered last, but very brief statements only. We are running out of time.
Yes, I want to second this. The really tough part of it is, in addition to sort of having a broader requirement statement, is actually getting data. There's a parallel problems in both SCTP and Quick and partial solutions. It turns out one of the lessons from Quick is that this actually matters a lot in certain parts of the internet and for certain applications. Having that data rather than speculating about why it's important will change this conversation. This has bugged me for 20 years, and finally doing something about it would be great. I think we don't know how much it hurts us.
Thank you.
Michael Tuxen from the floor. I'm not that much concerned about the security issue you raised, because as an attacker, I can always send you duplicate data, and I get sacks for each one. Giving you a hint how you can elicit an hack immediately, just duplicately transmit an old byte again. It costs you 1 byte more, and you get an hack.
Okay.
Gordon Fairhurst, I think we did something similar with SCTP in the IBIT, and before we charted that, we did lots of analysis of why it might be useful because we put back pressure on. So some of that analysis has already been done for SCTP.
Thank you.
Just very quickly, I agree with what Bob said. I don't think the mechanism here is necessarily the one that we want to use, but I think it's worthwhile doing a requirements discussion.
Thank you.
Just a clarifying point that delayed act timeouts are reduced now in most operating systems. It's no longer 200 milliseconds. It's down to like 40 or 50. So the impact of delayed act timeout is less now compared to before. The second point I wanted to say was, so if the receiver wants to indicate a hint to the sender that there is no subsequent packets that are going to be sent, right? So in that case, that might be useful as a hint rather than a forcing mechanism.
Okay, thank you. Thank you for the feedback.
Thank you. This is then. You have questions? No. Okay. Then. Thank you all. This closes TCPM in Montreal. Thank you. 3 minutes longer than expected.